Guidance for on-stream and off-stream piping inspection based on API 570, API 574, and ASME Codes, standards-driven approaches for effective piping inspections. Introduction and Inspection Framework, Purpose, Scope, and Applicable Standards. This section establishes the purpose and overall framework for performing piping inspections in accordance with internationally recognized codes and standards, primarily API 570, API 574, and the ASME B31 series. The purpose of piping inspection is to ensure the continued mechanical integrity, safety, and reliability of piping systems throughout their service life. Inspectors play a critical role in preventing loss of containment, protecting personnel, safeguarding the environment, and maintaining operational continuity. API 570 provides the mandatory requirements for in-service inspection, rating, repair, and alteration of metallic piping systems. It defines inspector qualifications, inspection intervals, thickness requirements, and acceptance criteria. API 574 complements API 570 by offering detailed inspection practices, practical guidance, and illustrations that help inspectors understand how to examine piping components, recognize deterioration, and apply inspection techniques effectively in the field. The ASME B31 piping codes, such as B31.1, B31.3, and B31.4, form the design and construction basis for piping systems and are essential references when determining minimum required thickness, allowable stresses, and design conditions. Together, these standards create a comprehensive lifecycle approach. ASME governs design and construction, API 570 governs in-service inspection and maintenance. And API 574 provides the practical how-to for inspectors. This presentation is intended to guide inspectors in applying these standards systematically during both on-stream and off-stream inspections, ensuring consistency, technical correctness, and regulatory compliance while adapting to real-world operating conditions. Role of the piping inspector and qualification requirements. The piping inspector is a key authority responsible for assessing the condition of piping systems and determining their fitness for continued service. According to API 570, inspectors must be properly qualified, typically holding API 570 certification, and must have sufficient knowledge of piping materials, fabrication methods, damage mechanisms, and inspection techniques. Their responsibilities include planning inspections, identifying credible damage mechanisms, selecting appropriate inspection methods, and evaluating inspection data against code acceptance criteria. Inspectors must understand process conditions such as pressure, temperature, flow regime, and chemical composition, as these factors directly influence degradation rates and damage susceptibility. Beyond technical knowledge, inspectors are expected to exercise sound engineering judgment, especially when evaluating anomalies, corrosion trends, or unexpected damage. They must coordinate closely with operations, maintenance, and engineering teams to ensure inspections are conducted safely and efficiently, particularly during on-stream activities where systems remain in service. Documentation is another critical responsibility. Inspectors must ensure that inspection findings, thickness measurements, corrosion rates, and recommendations are accurately recorded and maintained in auditable records. Inspector competency also includes familiarity with non-destructive examination (NDE) methods, limitations of each technique, and awareness of human factors such as access constraints and inspection bias. Ultimately, the inspector serves as the link between code requirements and practical field execution, ensuring that inspection activities support safe, reliable, and compliant plant operation. Inspection philosophy and common piping damage mechanisms. API 570 promotes a risk-based and condition-based inspection philosophy that focuses inspection resources on areas with the highest likelihood and consequence of failure. Rather than inspecting all piping uniformly, inspectors are expected to identify and prioritize credible damage mechanisms based on process conditions, materials of construction, and operating history. Common piping damage mechanisms include general corrosion, localized corrosion such as pitting, erosion and erosion corrosion caused by high-velocity fluids, and various forms of cracking. Fatigue cracking may result from cyclic stresses, pressure fluctuations, or flow-induced vibration, particularly in small-bore connections. Environmental cracking mechanisms, such as stress corrosion cracking, may occur in specific material-environment combinations. High-temperature damage mechanisms, including creep and graphitization, are concerns in elevated temperature surfaces. Corrosion under insulation, CUI, is a particularly insidious mechanism, as it is often hidden and can progress rapidly under certain temperature ranges and moisture conditions. Understanding these mechanisms allows inspectors to select appropriate inspection locations, intervals, and techniques. API 574 provides valuable descriptions and visual examples that help inspectors recognize early signs of deterioration in the field. By aligning inspection activities with damage mechanism knowledge, inspectors can improve detection effectiveness, reduce unnecessary inspections, and support proactive integrity management. On-stream inspection definition, techniques, and safety. On-stream inspection refers to inspection activities performed while piping systems are in operation, meaning they are pressurized and often at operating temperature. API 570 allows and encourages on-stream inspection where feasible, as it minimizes production interruptions and supports continuous monitoring of piping condition. Typical on-stream inspection activities include external visual inspection to identify corrosion, leaks, deformation, coating breakdown, and support issues. Ultrasonic thickness measurement, UT, is the primary tool for assessing remaining wall thickness and establishing corrosion rates without removing piping from service. Profile radiography and real-time radiography may be used to detect internal corrosion or erosion, particularly in areas where UT access is limited. Inspectors also assess piping supports, guides, and restraints for signs of corrosion, misalignment, or excessive movement, as well as indications of vibration that could lead to fatigue damage. Safety is a critical consideration during on-stream inspection. Inspectors must be aware of hot surfaces, hazardous fluids, elevated locations, and restricted access. Proper permits, personal protective equipment, and coordination with operations are essential. Inspectors must balance thoroughness with safety, ensuring that inspection activities do not introduce additional risk. Effective on-stream inspection enables early detection of degradation, supports timely intervention, and extends the safe operating life of piping systems. Off-stream inspection definition, techniques, and coverage. Off-stream inspection is conducted when piping systems are taken out of service, depressurized, drained, and made safe for internal access. These inspections are typically performed during planned shutdowns or turnarounds and allow for more comprehensive examination of piping condition. Off-stream inspection activities include internal visual inspection to assess corrosion, fouling, deposits, and erosion patterns that cannot be observed externally. Advanced techniques such as corrosion mapping, magnetic particle testing, MT, and liquid penetrant testing, PT, are commonly applied during off-stream inspections to detect surface and near-surface cracking, particularly at welds, fittings, and high-stress locations. Dimensional checks and alignment verification may also be performed. Off-stream inspections provide higher inspection coverage and greater confidence in piping condition, but they require careful planning, isolation, and safety controls such as lockout/tagout, confined space entry procedures, and gas testing. Inspectors must take advantage of the opportunity to validate on-stream inspection data, confirm corrosion rates, and identify damage mechanisms with greater clarity. Findings from off-stream inspections often drive repair, replacement, or alteration decisions and are critical inputs to future inspection planning and risk assessments. Thickness evaluation, inspection intervals, and fitness for service. Evaluation of inspection data is a core responsibility of the piping inspector. Thickness measurements obtained through UT or other methods are compared against minimum required thickness values calculated using the applicable ASME B31 design code. These calculations consider design pressure, temperature, material properties, joint efficiency, and corrosion allowance. API 570 provides guidance on establishing corrosion rates and determining remaining life, which are then used to set appropriate inspection intervals within code limits. When measured thickness approaches or falls below acceptable limits, inspectors must evaluate the piping's fitness for continued service. Fitness for service assessments. Often performed in accordance with API 579/ASME FFS 1, provide a structured methodology to assess the acceptability of flaws such as metal loss, cracking, or deformation. These assessments support informed decisions on whether piping can continue to operate safely, requires repair, or must be replaced. Proper evaluation ensures that decisions are technically justified, risk-informed, and aligned with regulatory and company requirements. Repairs, post-repair inspection, and record keeping. When inspection findings indicate unacceptable conditions, repairs or alterations may be required. API 570 defines requirements for both temporary and permanent repairs, including welding, mechanical clamps, and component replacement. Inspectors must ensure that repair methods are qualified, properly designed, and executed by competent personnel. Post-repair inspection is essential to verify workmanship and compliance with code requirements. This may include visual inspection, NDE, and pressure testing as applicable. Accurate documentation is critical throughout the inspection and repair process. Inspection reports, thickness data, corrosion rate calculations, repair records, and alteration documentation must be maintained in a structured and traceable manner. Effective record keeping supports future inspections, audits, and integrity assessments. Inspectors must also coordinate closely with operations and engineering teams to ensure repairs are implemented safely, efficiently, and with minimal impact on plant operations. Clear communication and documentation help ensure that lessons learned are captured and applied to continuous improvement of the inspection program.